Okay, then software interrupt. Okay, supervisor call. Okay, do I have to do it again from the beginning? Okay, so Minji. Minji? No? Okay. Susan? Okay. Okay, done. Okay. Supervisor call. That is software interrupt instruction. ARM CPU is providing. Okay, SVC. Okay, SVC instruction. And if you put SVC instruction in your code, I have a demo. So let me show you. So here, right, this is an example. So go to class page, and the first one, software interrupt. Okay, you can download it and create a project in Vitis. And this is example code. And if you scroll it down, I put this SVC, software interrupt instruction. Okay, so CPU execute SVC instruction, then this one will happen. It will happen. Okay, supervisor call. Program counter will be changed to 08. That means what? That means at 08 location. 08 location, you are supposed to put some code, right? Simple, same protocol. So IRQ, FIQ, software interrupt case, branch. Any name is okay, right? SVC, ISR. Okay. Then that actual interrupt service routine. SVC, ISR supposed to be somewhere in memory. Okay. And ARM CPU will be going to supervisor mode. If you remember, operating mode in ARM. Let me refresh your memory. So there are 9 different operating modes. Remember this slide? So 9 different operating modes, right? User mode, system mode, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 different operating modes. So IRQ happens, no more interrupt happens, then CPU will go to IRQ mode. Okay. FIQ happens, then CPU will go to FIQ mode. And software interrupt happens, SVC, you execute SVC, then CPU will go to supervisor mode. Typically, you are running your application program, main, right? Hello world, that is executed in user mode. User mode, right? It's user mode. Then interrupt happens, CPU will change it to IRQ, FIQ, or supervisor. Okay. So let me refresh your memory. So this is CPSR register. Here you have a mode bit. Right? This mode bit is defining which mode CPU is operating now. Right? So in case of, so let's check out this encoding. The user mode, right? If you are in user mode, mode field will contain 1 4 zeros. Right? 1 4 zeros. Then if you are in FIQ mode, 1 3 zeros and 1. Right? If you are in IRQ mode, 1 2 zeros and 1 zero. Supervisor mode, this value. Okay. And this column, next column is talking about privilege level. You have to understand that privilege also. Okay. So PL0, PL1, privilege level 0, privilege level 1, and 2. Right? and PL1 is lowest privilege. So that means you are executing your user program in PL0 typically. Think about Linux or Windows, right? There are system administrator and client, typical user, right? And system administrator root, right? Root are supposed to have all the power to change anything you want, right? In computer. Okay? That all the power comes with that privilege. You have to have that enough privilege to change anything you want in a computer system. But if you are in user mode, you have a very limited access to critical I/O device or critical the memory region. You are limited. Okay? So you have very limited access in user mode. That in PL1 you can do anything you want. Okay? So ISR is typically executed. So main is executed user program, right? That is typically executed in user mode, and it has PL0, lowest privilege. Then ISR. Okay? In ISR, you go to IRQ mode, right? Or FIQ mode, or supervisor mode. Okay? That is PL1. Then you have all the power to change anything you want in a system. Okay? So you are switching from PL0 to PL1. You are root, in other words, system administrator. You can change anything you want in PL1. Okay? So that makes sense, right? Different privilege. So Intel also implementing similar mechanism. Okay? Ring 0, ring 1, ring 2, ring 3. Have you heard about that? Ring 0 to ring 3. And Lec15 is also implementing same privilege, similar, right? Not same, similar privilege mechanism. So the thing is, every CPU is providing that privilege level. So user is running in lowest privilege, and system administrator or root is running in privilege level, higher privilege. So that switching back and forth is done. Right? So you are done, then you go back to user mode. You return back. Any questions so far? Does it make sense? Okay, let's move on. This one. Let's go to this place. This one is called exception vector. And in computer, some people. So I told you I had two different events in computer at the beginning. Interrupt and exception. The first one, interrupt, the second one, exception. So I want to differentiate these two events. But some people do not differentiate these two. Some people just say interrupt. Some people just say exception. They do not differentiate these two. But I think it makes sense to separate these two events. So interrupt typically generated from I/O devices, and exception. One good example of exception is undefined instruction. Undefined instruction. The exception is happening while executing some program inside the CPU. So this is an undefined instruction. Think about that. CPU is reading machine code, right? Reading machine code and executing. What if hacker changed it? So originally that instruction was addition R1, R2, R3, and hacker sneak into your system, flip the bit in the machine code, and CPU catch that instruction, trying to execute it. But hacker changed operation code field, OP code field. So CPU does not understand that instruction, cannot interpret that machine code. So that is called undefined instruction. CPU, okay, I don't know that instruction. That is the exceptional case, exceptional event. So there is one example of exception. So I want to separate these two, interrupt and exception. But in ARM, look at this. Exception vector. ARM is not differentiating for these two, just to say exception. Exception. So here, don't worry about these three columns: monitor mode, secure, and non-secure. You are in secure mode for now. We will talk about that secure, non-secure mode or world, secure world, non-secure world. When we talk about security feature in ARM CPU, that is called trust zone. That is the last topic in this class. Okay, so we are going to talk about secure mode, secure world, non-secure world, or secure world, normal world, secure world, normal world. Okay? And monitor mode is the gatekeeper. You have to go through that monitor mode for switching between secure and non-secure. You have to go through that monitor. But don't worry too much about this. Focus on this, that the column in the middle. Okay? Secure mode. So when you turn on Jetboot, you are in secure mode. Okay, you are in secure mode, and there is exception vector, or we call that interrupt vector table. This one is interrupt vector table. Look at this, right? Location 8, you have this vector. This it sounds like vector. You go to this place. Okay, branch IRQ ISR. You go to that place. It sounds like a vector. Right? Here you go to that place. It sounds like vector. You have collection of vector, different vectors. Right? That is called interrupt vector table, IVT, or in ARM terminology, exception vector table. Interrupt vector table or exception vector table. Okay? So we are talking about the steps you have to take to go to actual ISR. Okay, we have IRQ ISR. This IRQ ISR. Okay, what kind of steps you have to take? You have to check out IVT, interrupt vector table, or exception vector table to get to this place. Okay, IVT to get to this place, vector table. Okay. So we have different vectors here. So that is talking about interrupt vector. When you turn on computer, reset, right? You press the reset button in Jetboot or computer, in ARM smartphone, right? Smartphone. Then CPU will execute the instruction at that location. What location? 0. Right? So location 0, you are supposed to have some instruction. That is typically branch. Reset, ISR, or empty is okay. Reset code. Right? So reset code is supposed to be somewhere in memory. Right? Memory you have reset ISR. Okay? So reset vector. Okay, and look at this undefined instruction. CPU hit undefined instruction. CPU does not understand, right? This exception. Undefined instruction. CPU does not know, right? CPU cannot interpret. Then CPU will change program counter to 4. Okay? That's 4. This 4 offset. Okay. So that means you are supposed to put some code. 0, 8, 0, 4. Branch undefined, right? Any name, undefined ISR, undefined exception handling code. That's supposed to be somewhere, right? Somewhere. Right? 0, 4, 8. Look at the numbers. 0, 4, 8, C. Right? 4 difference, right? 0, 0, 4, 8. C is 12 in the decimal, right? 10, 14, 18, 16. So 4 difference. So you can place only one machine code, one instruction here. because each ARM instruction is 4 bytes in size. Right? 4 byte, 4 byte, 4 byte, 4 byte, 4 byte. Okay? So that is interrupt vector table, exception vector table. Okay. So any question about this? This is super important information. Some detail, but ARM specific detail. But you know, every CPU is defining interrupt vector table structure, their own IVT structure. Intel CPU has their own IVT structure. RISC-V has their own interrupt vector table structure. ARM their own vector table structure. Okay. So silent, understandable. Okay, silence is not good sign, right? Don't understand or completely understand, but don't understand anything. Now, Camden, what do you think? No problem. Okay, Vera, you here? Vera, Aira, any question? No. Okay, let's move on. Okay, and this is the operating mode I mentioned, right? Reset, turn on Z boot, then ARM CPU will go to what? ARM reset, right? ARM CPU will go to supervisor mode. Okay, and undefined instruction. There's undefined mode. If you recall, look at this. There is undefined, right? Undefined mode. Undefined. Okay, undefined mode in ARM, right? And this abort, don't worry too much about this abort. We will talk about that. There is also one kind of exception, not interrupt. Okay, two kinds of event, interrupt, exception. Okay. Undefined instruction is one category of exception, and abort, prefetch abort, and data abort are two different. Other two different exception events. Then IRQ and FIQ. IRQ and FIQ. So there is an abort mode. If you go to the table, abort mode, right? Here. Abort mode. Okay, then let's talk about very important system register you have to know for defining your own interrupt vector table. We want to define our IVT, and let CPU know the start location, start IVT, right? Start location of IVT. Okay, so system register VBAR is providing that capability. This one. Q1. Okay. Done. No time for break for me. Okay. So VBAR register. The name stands for vector, right? Vector base address register. Vector, right? Vector, IVT. Vector base, the start location. Okay, start location. So VBAR register. Probably you want to take a look at to access VBAR register. You have to write this MRC and MCR instruction. We haven't studied that instruction yet, but that is you don't have to understand that instruction. Just use that instruction in your code. What do you mean by that? Too complicated. Okay. So to read VBAR register and store into general purpose register, simply use that instruction. Okay. Do not try to understand the code. Just to use that instruction. Right? Then how come you know that instruction? simple. Take a look at this arm. PRM. Okay. I should download it to the computer. Taking too much time, I guess. How to download, Juan? This PDF to the desktop, Juan. Download where? Oh, this one. Okay. Download it to desktop. Okay. So here, search with V bar, right? Search with V. Okay, then not this V bar, H V bar, not this V bar, just V bar. Okay, this one. Then this page is talking about V bar register and explain the purpose. Then example code at the bottom, right? So to read V bar register and place into R0 or R1 general purpose register, simply use that instruction MRC. Okay, so it stands for coprocessor. MRC means MRC. C means coprocessor register. Coprocessor register to general purpose register. We have R0, R1, R2. So V bar to R0. You want to read V bar to R0, R1. And to update opposite operation MCR, MCR from general purpose register R0, R1, R2, R3 to coprocessor V bar. V bar. So you want to update V bar register with that instruction. And this operand is too complicated. Okay, do not try to interpret that operand. Okay, it is not words. Okay, so simply place any register you want, right? R0, R1, R2, anything. Okay, so use MRC to read V bar register and use MCR to update V bar register. Okay, so if you check out this example code, then I wrote this code, right? So I prepared my own, look at this. I prepared my own interrupt vector table in the example code, okay? And that is the start location, base location, right? So 0, 4, 8, C, 10, 14, 18, 1C. Interrupt vector, yes, Camden. Can hear you 4-bit?
Does it automatically set it that?
Oh yes, because each instruction is 4 byte size, right? Instruction, ARM instruction, this branch instruction. This branch instruction is 4 byte, that branch is 4 byte, and so on. Right? Okay, thanks. So here we define our own interrupt vector table using that instruction. Okay, LDR, right? LDR, location of that vector, location of that table. Okay, R0, then R0 and R0. We use MCR instruction. See MCR, right? MCR register to vector base, update vector base. So using that instruction, we are updating V bar register. Then CPU now know, okay, interrupt vector table start from that location. Start from this location. Which location? That location. So compile it and check out this ELF. Then you can search it. So vector table, right? Compiler placed vector table from that location 120,580. Okay, that is the start location, our interrupt vector table. Okay, so using MCR instruction, we are able to define our own interrupt vector table. And this one, MRS, MSR, we haven't studied those instructions, but you can just take a look at this slide, ARM instruction slide, right? And scroll it down, go to the end. And I like you to study. I don't want to explain. Using MRS, now you understand, right? MRS, MSR, you can change, you can read CPSR register. CPSR, right? Current program status register. In ARM, we have what? We have general purpose register from R0 to R15, okay? And we have CPSR, current program status register. So good news is your status register, not only ARM. This is ARM specific status register, but every CPU, Intel, RISC-V, you name it, MIPS, everything. Every CPU is providing status register, similar function. So many aspects are common. Every CPU has general purpose register, CPSR, a status register, and some system register. VBAR is also one VBAR. This one is called system register. This one, system register. You can access, it's a system register using MCR or MRC. And to access the CPSR, you use MSR, MRS. To access CPSR, to read, okay, it is status, right? S2R. You want to read CPSR to general purpose register. And opposite operation, register to CPSR. You want to update CPSR with that instruction. Using MRS, MCR, MSR, you can read CPSR or update CPSR. Okay? So that means you can change. This is a CPSR. You can change mode bit. You can change I field, F field, T field, anything you want actually. If you have all the power. If you have enough privilege, okay? If you have a PL1, if you are root, not user, right? If you are root, then you can change anything you want. CPSR. You can change operating mode. Okay? Using MSR or MRS instruction. Examples? Examples are, this MRS, right? So MRS R0, okay? R0 register and update CPSR, everything. So you don't have to have this underscore all, just to use CPSR. I think that is okay. And take a look at this. Again, the last one. I'm trying to. Spotlight. Okay. So using that code, okay. Using this code, I'm trying to take a look at this code. What do you think it's doing? So first instruction, read. Okay. First instruction is reading MRS R0 CPSR. So you are reading CPSR and place into R0 register. Okay, next instruction, bit clear. Bit clear. We haven't studied bit clear, but simple operation. R0 with what? Hex 1F. 1F 5 bits. Right? So you want to clear, bit clear last 5 bits in R0 register. So you have CPSR register in R0, okay? And you want to clear last 1F. Right? That means 5 ones in binary. So you want to clear last 5 bits, clear, make it 0. What is the field? That is mode bit. Remember? 420 in CPSR register. You want to clear that mode bit. The next instruction, OR operation. ORR, R0, then 13. So you want to place only 13 into this place. 13 is what? 13 is, I think, what is that? 13. Okay, the comment, supervisor mode. If you check out the encoding. Encoding. Supervisor mode, right? Here you have 1, 2 zeros and 2 zeros. So 1, 3 in hex. Right? That is supervisor mode, right? So we want to place 1, 3. Okay, 1, 3 here. Then next instruction, MSR. The last instruction is updating CPSR register with R0. You have here. That means you want to change operating mode to supervisor. You want to touch. You want to replace that mode bit in CPSR with 13 supervisor mode. So you can either use this sequence of instructions or there's a shortcut. You can use CPS, simple instruction. ARM is providing very simple instruction, CPS. This one, okay. Okay, change processor state. You can use just one instruction to change mode bit, mode field, or to change. Remember, in CPSR register, you have mode field, AIF field. Okay, let me show you. Here mode field, right, CPSR, and you have AIF field. I field means if you set I field to 1, that means what? CPSR you have mode 5 bit, then AIF. If you set this bit to 1, I bit to 1, that means you are masking interrupt. That means CPU will not take interrupt. CPU will not take interrupt if I bit is set to 1. You are masking, right? Even though IRQ line goes up, CPU will ignore that event. Okay, CPU will not process that interrupt. Okay, and F bit is set to 1, then that is related to FIQ input. Even though that line asserted, that line goes up, event happened, the CPU, okay, I'm not going to take that interrupt. So you can change I bit, F bit, A bit, and mode bit with the CPS instruction. Change processor state. One simple shortcut. Right? So instead of using 4 instructions, you can use just CPS instruction to change that CPS. Right? So here, so syntax. If you want to simply change mode field, the first instruction CPS to 113. Sorry, 13. Then supervisor mode. Then you can add some suffix, okay, IE. That means interrupt enable. So here you can add either of these two, interrupt enable, interrupt disable suffix at the end of CPS. Then you can specify here which field, A bit, I bit, F bit, which bit you want to enable or disable. You can specify. So take a look at this slide. Okay. So shortcut to change CPSI. What else? Okay. Before showing you a demo. Okay. So let's move on. This is super important. This one is that requires some explanation. Very important slide. This one. Okay. Let's think this. Okay. ISR and so you are making transition to ISR. After executing ISR, you are going back to this usual program and continue executing. That is execution flow. Interrupt happens here. Okay. Then to write ISR, interrupt service routine. So people think in industry, right? People think writing interrupt handling program is too difficult. So why? Because that handling program is not entirely. It cannot be entirely written in software. You have to understand hardware mechanism to write interrupt handling code. Okay? It is like collaboration between hardware and software. Hardware is doing very minimum amount of operation. Okay? Then the rest should be done by software. That is, somewhat confusing point. Okay? That is why people think writing interrupt service routine, interrupt code is very confusing. Okay? Because they don't understand what is happening inside the CPU while making that transition. Okay? Then hardware is doing, CPU is doing very minimum, but very essential amount of operation. Okay? And that is listing that essential and minimum amount of operation CPU must do. Otherwise, we have some problem, correctness problem. If CPU does not do that kind of operation, we have some problem, really. Okay, correctness problem. Okay. So what kind of operation CPU is doing in ARM case? The first one is take a look at this, right? Main program you got interrupted here, right? And you are eventually, after executing ISR, you eventually supposed to come back. Okay, so from user program point of view, hello world program point of view, actually nothing happened, right? CPU my program kept executed until to the end without any interruption. Even though physically there is an interruption, my program should be executed as if nothing happened in between. Okay. That means what? That means what? You have some status. Okay. So you have to preserve that state. Okay. Even though your CPU is processing ISR, you have to preserve the state. Then the program should be executed from this interrupted, the same state, right? So the question is how to preserve the state. What kind of information you have to save, right, to preserve the state. Okay? And the first one is CPSR, right? Current Program Status Register. CPSR should be backed up. So that is why you have SPSR register. CPSR, Current Program Status Register, that is saved in SPSR by hardware. I'm talking about what CPU, hardware is doing. Okay? So CPSR is saved in SPSR. Okay? Then you are free to use CPSR. The reason why we back up is because we are going to change operating mode. Remember, typically, the main hello world, this program is running in user mode. PR0, user mode, right? User mode. And M bit is, if I remember correctly, 10, mode bit. Then here, you are supposed to execute ISR in privileged mode, right? PR1 or higher, right? And mode bit, M bit, supposed to be what? Depending on event, IRQ mode, or FIQ mode, or supervisor mode, depending on event. So CPU will change. CPU is going to change CPSR. So before changing CPSR, that register should be backed up. Okay. So last one, take a look at that. So this third bullet, okay, mode bit will be changed. Right? So before you change mode bit, CPSR should be saved. Okay. And second operation CPU is doing, hardware is doing. Okay. The return location, CPU should save this return location. And CPU, hardware only knows that return location. Think about that. The software does not know. You don't know when interrupt would happen, right? Here, it is asynchronous event. CPU does not know. Computer does not know when you type your keyboard, when you move your mouse, right? Computer does not know, right? Asynchronous event. So when event happens, only CPU know. Okay, I'm executing addition instruction now. So if I resume, then I execute next instruction. Only CPU know, right? So that location will be saved in link register by hardware. That must be done by hardware. Software cannot do that operation. Right? So that is second bullet. The return location should be saved. And then the rest is basic. Third, mode bit, right? CPSR M bit will be changed depending on the interrupt, what kind of interrupt happened, right? So IRQ or FIQ or supervisor and so on, right? And then next one, CPSR I bit, interrupt mask bit will be set to 1 by hardware. So what does that mean? That means, so I told you, right? If you set I bit to 1, that means you are masking interrupt. That means while executing ISR, CPU say, I'm not going to take additional interrupt. I'm busy, right? I'm busy servicing interrupt. I'm not going to take additional interrupt. So then, CPSR information will be changed by hardware. So before that, you have to save, right? Before save, right? You preserve this state. In the last one, program counter PC should be changed according to the protocol I explained, right? We have interrupt vector table, right? IVT structure, right? So depending on interrupt or exception type, 0, 4, 8, or 1C, and 0 also. If you count reset, 0, 4, 8, 1C, depending on exception or interrupt type. Okay? So that whole operation, this operation is done by hardware. So to write interrupt handling code, you have to be aware of that operation. This operation is done by hardware. Then the rest, the remaining task, should be done by software. And that is a bare minimum amount of work must do by hardware. Otherwise, we have correctness problem. Computer system will not work correctly. So that is operation. The thing is, these two are important operation, right? CPSR backup, then return location. Return location is saved in link register. Then PC program counter, program counter will be updated. And at the end, what do you have to do? At the end of ISR, you have to come back. Then what do you have to do? What do you think? Opposite operation, right? Opposite operation. So the thing is, the first one, you saved, right? So SPSR is used to update CPSR. The first one, right? Second. Okay. Then program counter. Now you updated the state, right? And then second, program counter should be updated with the return location you saved here, right? LR. That these two operations should be done by what? Hardware, but you have to put some instruction. What instruction? Typically, so this one, the time. I want to show you a demo. So probably we don't have enough time. So you have to put something like move PC LR. Look at this. What do you think? If you put move PC LR, do you think that is enough to do these two operations? What do you think? Not really, right? So that instruction is updating only PC, right? This one is doing only that operation. So then to let CPU to do that operation, first operation, what kind of code you have to write? Simply put S. Move S. Okay. So that is one confusion point. Let me take some time to explain. It's really confusing. The rule is okay. Let me show you. Let me give you some code. So remember addition instruction, right? R1, R2, R3. Simple operation. So that instruction is doing that addition, update R1 register. What if you have S suffix? S. The instruction is doing first R1 update. Okay, and second, what? NGCD, right? Flag update. Update because you have S suffix. Okay? So that is what we studied. If you put S, then flags will be updated. Okay, that S is different from that S. Yes, if destination is not program counter. If destination is program counter, the S suffix has a special meaning. updating program counter is a super dangerous operation. Right? Think about updating program counter. You are changing execution flow to other places, right? Other place, right? So if you put S in the instruction and the destination is program counter, it is not updating flags. It is not updating, not doing this, right? So that is doing CPSR update. So you can use, so that is one important thing. So you can use either this or probably you can use that instruction addition to return. To return, you can use add S. How about this? PC, LR, then constant 0. That is okay. Okay, right? Destination is program counter. You have S suffix. That means it is doing first addition operation, right? PC, LR plus 0. Second, not NGCV update, not flag update. You have S destination is PC. Then CPSR update from SPSR. Okay, so or you can use this sub S, right? PC, LR, anything is okay. You have a PC destination as a suffix, but this instruction is not updating. It's not only updating, not updating NGCV. It is completely updating CPSR. So here we have an NGCV, right? NGCV that manually is not there, right? So that operation. You have to differentiate, these two instructions. A little bit confusing point, right? These two, S. Okay, then one more confusing point is what kind of instruction to use if you want to return from function, not from interrupt service routine. What if this one is foo, normal just function foo? Okay, you are calling, right? You are calling branch and link foo. You are calling this foo, then you want to return back. Then what instruction would you use? Move, just move, right? Without S. Right? Without S here, without S. Just move. So you have to differentiate these three, right? So return from exception, return from function, and the meaning of this S suffix. Okay? Don't be confused. This is a really confusing point. Okay, let me show you, quickly show you a demo. So here, that is why if you scroll it down, so that is, right? So I prepared this interrupt service routine for software interrupt. Okay, so here, vector. Software interrupt vector. Okay. Then CPU will branch to here. Then at the end, I put that instruction. To return from exception, move S. Then destination is program counter. So let me quickly download it too. So the code is very simple. Every time I execute this code, then I want to toggle LED on Z board. Try to interpret that. Okay, I can explain next time more detail, but let me just show you. Okay. Okay, here. So again, then I will press F5. Okay, I'm updating vector base register to use my own vector table, its own vector table. Okay. So don't worry about next to DSB, ISB. Don't worry about that. And changing operating mode to, so this is an example. This is one option you can use to change operating mode. Okay, operating mode, or you can use either this or simply shortcut, right? CPS. Just the example. Right? So here, F5. Then what do you think if I press F5? Software interrupt instruction, right? So then CPU is supposed to execute this. Let me press F5. Right. CPU read the vector, right? Located at 0x, 08 position. 0 position, offset 4 and 8, right? Then branch, right? Software interrupt. Branch, right? So ISR. Then here I'm pushing a context. So hardware is saving only CPSR. So before executing main, before using general purpose register, here R02, R12, then I need to push context. Right? This main program is using CPU context to the memory. Then at the end of doing this ISR, then I need to pop, push and pop. Right? So that is main. Then you are free. You push to memory, the context. So you are free to use R02, R12. Right? So that is the operation. So we are pushing, okay, then pop. So in the middle, I'm toggling LED. If I press 5. So here, this one is turning on LED, like this, or LED. Okay. So going back. So now, okay, forever, I return back to the usual program, and about to execute next software interrupt. Then same, right? Toggling like this. Okay, keep executing this code. Okay, I'll explain detail of this code next time. Continue. Okay. Any question before let me go? All right, that's it. See you next time. 안 돼. 코로나 사유가 있지 않으면
And here you said this is what if I'm higher? Here you said it's one.
Yeah, IB.
There is no.
But if you said IB to one, only nobody So fast interrupt happens, and that will be taken care of by CPU. So you are masking only normal interrupt in this case. Depending on interrupt. Yes. How's book?
저희 과제 C 프로그램을 제출해야 되잖아요. 그러면 그 C 프로그램 안에 아무거나 선물을 둘 다 작성해놓고 비교를 한 번에 하면 되나요?
그렇지. 첫 번째 컴파일할 때는 암모드를 컴파일하고 그다음에 시스템을. 그래서 인스트럭션이 얼마나 되고 비교가 얼마냐고 비교를 해서.
How does, like, from let's say a prompt, how does the CPU recognize which mode CPU should use?
Yeah, so depending on this input, right? So that interrupt is coming in through this IRQ, then mode bit will be changed to IRQ.
So does it come from like a instruction or something, like from the IO itself?
IO itself, right? So in the schematic diagram, in this simple schematic, we assume keyboard is connected to keyboard output is connected to the same.
Oh, it's like hardware connection.
Hardware connection, actual connection, physical connection. Yes. We'll talk about that throughout next time.
데모에서 보여주신 소드에서 그러니까 V발을 커스텀으로 만들어 놓고 그 ISR을 정의를 해놔야 쓸 수 있다.
그렇죠.
아, 프리디파인이 안 돼 있죠.
그러니까 지금 우리가 만드는 시스템은 우리가 다 모든 걸 알아서 하는 거야. 만들어준 게 아무도 없어. 그러니까 벡터 테이블도 우리가 만들고 핸들링 코드도 우리가 만들고 다 우리가 만드는 거야. 누가 해주는 게 어딨어. 생각을 해보면 소프트웨어를 짜는 건데 PC에서도 누군가가 그걸 마련을 해놓은 거지. 근데 우리 시스템에서는 아무도 해주는 사람이 없어. 우리가 다 하는 거야.
그 다음에 그러면은 그 시퀀스알 모드가 자동으로 하드웨어에서 바꿔준다. 그거는 벡터 테이블을 보고
아니지. 그 전에 인터럽트 어떤 인터럽트 타입이냐에 따라서 모드 빛이 바뀌는 거지. IRQ 인터럽트가 이거 얘를 타고 들어와서 걸렸다면,
네.
그러면 IRQ 모드로 바뀌는 거지.
아, 와이어를 보고
그렇지. FRQ 요 선을 통해서 들어오면 FRQ 모드로 바뀌는 거고, 슈퍼바이저 모드는 그거잖아. 인스트럭션이니까.
네.
SVC. 그거는 CPU가 알잖아. 아, SVC를 수령하는 중에 걸린 거니까 슈퍼바이저 모드로 바뀌는
아,
수업용은 좀 간단하죠. 모드가
그러니까 동작 모드별로 LR이 따로 있잖아. 여기 보면 여기 R14는 L14는 동작 모드별로 따로 있잖아요. 레지스터 물리적으로. 그래서 그 레지스터를 업데이트하는.
혹시 이 테이블 보면은 인터럽트도 익셉션 일종이라고 봐도 돼요.
그러니까 이제 사람에 따라서 인터럽트와 익셉션을 구별하지 않고 통으로 그냥 그냥 다 인터럽트라고 얘기하는 사람도 있고, 두 개를 합쳐서 그냥 익셉션이라고 말하는 사람도 있고, 근데 이 클래스에서는 두 개를 구별을 하려고 해요. 그게 좀 맞을 것 같아요.
네. OS 할 때 좀 OS를 하게 되면 PC가 업데이트되고 그다음에 SPSR이 다시 튀어나오고.
그렇지. 무브 S를 하게 되면 단 조건이 있어. 데스티네이션이 PC. 그때는 첫 번째가 당연히 PC를 업데이트하는 게 당연할 거고, 그치? 요걸 하라고 했으니까. 근데 S가 있다면 그러면 아까 요 동작을 했다.
그럼 만약에 OS 안 쓰고 하기 전에 이제 MRS 같은 거 써가지고 SPSR을 로딩해서 수동으로 넣고 그냥 무브 PC 에러를 해도 똑같다고 볼 수 있나요?
그러면은 문제가 생길 소지가 있어. 그거는 좋은 질문인데 아주. 그러니까 얘를 우리가 이 인스트럭션을 실행하면 이거는 우리가 이런 말을 쓸 수가 있대. 이렇게 갈 때 애토믹하게 실행이 된단 말이야. 이거를 브레이크할 수가 없어. 이걸 하고 이걸 하는데 중간에 만약에 어떤 이벤트가 발생.
네트워크가 끼어들었다가 거치는 망가진다.
망가졌어. 뭔가 이벤트가 발생할 수도 있잖아. 그러니까 이 두 개를 만약에 소프트웨어 이거 안 쓰고 인스트럭션을 쓰고 더 갖고 똑같은 응답 시키겠다. 여기서 중간에 브레이크가 될 수도 있고. 그럼 문제가 생겨. 아주 좋은 질.
그러고 그 아까 코드 중에 제일 밑에 B.다 이렇게 키웠는데
자기 자신.
계속 도는 거.
자기 자신. 그 머신 코드를 보면 자기 자신을 쏜다. 그랬잖아. 어디요? 대학원. 제검 보고 싶다고?
가능한 거
그래. 지금 가죠.